So I said a couple of minutes ago that you all agreed that the Copenhagen interpretation was insufficient, but the next part of David's story was that after sort of determining this and shelving it, you all ended up with completely different intuitions about which theory of quantum mechanics was in fact the correct one. And I would like to get more specifically to Bohmian mechanics in a little bit, which of course I talked with Shelley about, but I'm wondering if there is something before the adoption of Bohmian mechanics that you can identify as maybe there are multiple things that are the cruxes that resulted in all these diverging views.
Yeah, let me just correct, I think, the language. I don't think
Please.
correct is the right word there. Most promising, right? There are different approaches. We all understand none of them have been completed to the level they would have to be.
Okay.
And you have to make a decision, not which one is correct, but, where do you, which one seems to you, and there's a certain amount of subjectivity in this. Now, we've been through, I've got this kind of triage, which I think Shelley agrees with, that you either have to add additional variables, which you can do without disturbing the unitary Schrodinger evolution of the wave function. That's the kind of Bohmian route. You can put in objective collapses. That's the GRW route, or what Penrose is doing, or you're stuck with many worlds. It's got to be one of those three. And I think the only real difference between David and us was David thought that the objective collapse theories would allow you to derive everything you thought of as probabilistic, including thermodynamics and other places where probabilistic notions come in, from one theory. He used to say that, right? That it would unify in a certain way the probabilities that show up in quantum mechanics and the probabilistic reasoning that shows up in statistical mechanics and so on. And he thought that would be an interesting unification and simplification. I always found collapse theories, although I understand if you put the collapses in a rigorous way, you can try and make them work. They never felt right to me, right? This kind of dual dynamics never felt right to me. So I wasn't tempted in that direction in the same way. But again, I think I can appreciate other reasons for looking in other directions. Tell it, Shelley. I don't, how.
I agree with that. Yeah, here's the thing when you're working in, particularly, I guess, in foundations of quantum mechanics, you encounter all kinds of theories. Most of them don't make any sense at all, even though they get published. Then you say, okay, I'm not going to pay any attention to these that don't make any sense. Then you have some which sort of make some sense, and you say, well, how well do these theories do? And sometimes you find theories which do very well in explaining all the facts. They sort of make sense as theories, and then you try to judge between them. That's the way that's how the science should have proceeded. Nonetheless, it's not how it generally proceeds. Most practitioners, particularly physicists, I would say, tend to dismiss the theories that they're not proponents of without trying to understand them properly. Quite the opposite. They want to find reasons not to understand them. They use their great intelligence to find reasons to reject rather than to understand in situations where they should not be rejecting. This is all too common. It's aspect of human nature.
Tim, I hadn't heard the viable theories reduced to those three that you mentioned: hidden variables, GRW, and many. Well, maybe not GRW in particular, but
that's just a little that's an argument I gave many years ago in a little paper called Three Measurement Problems, and it's just, I thought we went over this. I don't know. I've done too many interviews. There are three propositions that are mutually incompatible. You can't hold all three. One, the wave function is complete. Two, the wave function never collapses. And three, experiments have unique outcomes of the kind you think, like the one cat you started with ends up either alive or dead. It's kind of easy to prove that you can't hold all three of those. And so then you can triage propose solutions by which one or ones. You could give up more than one, but mostly people want to keep all three. So if you can give up one and get away with it, you tend to do that. Which of those three are you going to give up? I mean, this is the first question you should ask. If somebody says, I have an understanding of quantum phenomena, the first thing you should say is, well, do you believe the wave function is complete? Do you believe it always evolves by Schrodinger's equation or some linear equation? Are you a many worlds person, right? And if they answer no to all of those, then you know they're confused.
You probably know they're confused no matter how they answer it. I mean, because the way they answer is going to be all over the place. Confusion is par for the course. By the way, since three is a more complicated notion than two, a corollary of Tim's observation is that if you insist, as many physicists would like to do, that the wave function must evolve according to Schrodinger's equation, then you have only two options. Either the wave function is everything, many worlds, or the wave function is not everything, there's other things. And that basically leads most naturally to Bohm. That's a very, very simple set of possibilities. And you would think that would be really clear. So I'm actually struck by the fact that so many people that I talk to, really intelligent people, who do want to say that the Schrodinger evolution is the fundamental evolution equation, but they don't. But they also insist they don't want to be Bohmian or have hidden variables, anything like that. But they say they can't make any sense of many worlds, and they wonder why would anybody believe in many worlds. This I find interesting. It just says the psychology is often more interesting than the physics.
Mm-hmm. Well, my psychology as somebody who's not a physicist, I think I fall into this camp, and my response is, how could anybody believe in many worlds because of how inflated this ontology is into a multiverse? But when I talked to Sean and David about this, they said that to them, this is a non-issue. The main concern is probability, making sense of probability.
Look, I think I would have to actually say their response there is fine. Look, this is in common between many worlds and pilot wave. You've got a wave function, you've got a quantum state, which is a physical thing described by this mathematical wave function. And it always evolves by Schrodinger's equation or some linear evolution. Okay, that alone, given how it evolves, is going to give rise to this tremendous, diversity of, and you can pretty much define what you mean by decoherence. It's going to give rise to this tremendous diversity of decoherent parts of the wave function, these things they call branches. You don't postulate them, as a separate postulate. That's just a consequence of allowing the Schrodinger evolution to just do what it does, right? So they're going to say, look, I haven't, what did I postulate? In fact, one thing they can say correctly is that their ontology is very sparse. It's only the wave function and only doing this very simple thing. So I don't think there's a kind of Occam's razor. I'm not very fond of Occam's razor at all in any case, but I don't think there's any Occam's razor criticism of many worlds. What I thought for a long time was the main problem was probability. What Shelley opened my eyes to is that there's a much deeper problem, and you also see this in Bell, and you can read Bell's paper, The Theory of Local Beables, which is if all you've got is the wave function, and the wave function is not a local kind of thing in space-time, and if all of our empirical evidence is stated in terms of the behavior of local things in space-time, there's a gap there you really need to fill, right? How does your theory bear on what we take the evidence to be, right? I mean, the language, and this is where Bell praises Bohr, of saying the experiment has to be described in classical language. That's local stuff in space-time. So if you don't know how to make a connection between your fundamental physical postulates and stuff going on kind of in a familiar way in a three-dimensional space-time at macroscopic scale, then you don't know how to connect your theory to what we take evidence to be. And that's a really bad problem. That doesn't mention probability. That's a much worse problem, a much more fundamental problem.
And Robinson, what Tim said is so simple and obvious that it's difficult to appreciate because it sort of sails under the radar. It's important to really digest that something so simple can be can be focused right at the issue.
Mm-hmm. Yeah, it seems like this is also a place where very basic concerns about ontology in the form of local beables really weigh heavily in what I will label the interpretation wars.
Mm-hmm. Absolutely.
Yeah. And is this then the basic crux of what motivates the two of you to adopt the model where there's not just a wave function, but a particle configuration, so that there are, in fact, these local beables?
Well, I mean, let me just say this again. I'm always just channeling things that Bell says, but I'll say it again. There's this term hidden variables that comes up, right? And Bell says that calling the particle positions in a pilot wave approach the hidden variables is a piece of historical silliness. And the other thing he says, which everybody agrees, is if you believe there's this quantum state, this wave function, this thing described by the wave function, it's really hidden. I mean, it's really hidden. If I hand you an electron and I tell you this electron is in a specific eigenstate of spin in some direction, some particular direction, I just prepared it so it's spin up in a specific direction in space, and I hand you the particle, and I say, do your worst, right? Do any experiment you want and try and figure out what quantum state it's in. What everybody will say is you can't do it. That cannot be determined empirically. That cannot be determined experimentally. The wave function cannot be seen in that sense. The only reason you have to believe there is a wave function at all and what it is because of the influence it has on things you can see, like where spots appear on screens. That you can see, but you cannot see quantum states. So if you start from there, the idea that, oh, I'm perfectly happy with there just being a quantum state and I don't want to mess it up by adding anything else, that just doesn't make any sense. Because the thing you're perfectly happy with is the thing that is hidden, right? It's not accessible. It's not directly accessible. And if you don't have anything else, then this is just another way of saying you're in a heap of trouble. Right?
When you don't have to be at all original or do any kind of systematic analysis to say, in non-relativistic quantum mechanics for a system of particles, you're really dealing with particles, things with positions. The very language, the whole discussion in quantum mechanics seems to suggest that you've got particles. It's not that you have to be really clever and introduce hidden variables. You just say there exist the obvious things. Let's try that. It happens, that works perfectly. Why so few people tried it is a big mystery. You say the obvious thing. I really have particles, not just the wave function. I've got particles too. And they move in a way which is naturally suggested by Schrodinger's equation and the wave function. And out pops all the predictions, all the mysterious predictions of quantum mechanics, randomness and all.